Good morning, guys. Welcome back to the channel. So what's up with my camera rig? What am I doing? Well, today we are going to focus on the Scan My Tesla app that I've got on my tablet computer in front of my cut-top steering wheel there. And I wanted to go through specifically battery voltage sag under load. So I think you guys are going to get a kick out of this video. It's something that I've been wanting to do for some time, and it gets a little bit technical, but by all means, stick it out, watch the video through, and I think you'll learn something. If you don't want to watch the video all the way through, basically, a brief summary is if you pull a lot of current off the battery, the voltage sags, and that's hard on the cells. Pretty much it. But I want to explain what I mean by that and show you some data on the Scan My Tesla app. So I think you'll get a kick out of this. So let's go ahead and dig into it. Hey guys, welcome back to the channel. So for today's video, I wanted to do some more delving into the Scan My Tesla app. And so I've got my camera set up aimed at my tablet and in front of my steering wheel here on the dash. And I set up a custom screen, a custom layout, which is just battery voltage and kilowatts of rear motor power. So I wanted to explain voltage sag and how it pertains to battery longevity and vehicle performance. So if you'll watch, see how the battery voltage is 391, and if I floor it, watch the battery voltage sag down to 338 volts. So that voltage sag, or that is what's known as voltage sag. Voltage sag is indeed what its name would imply. It is the sagging of voltage, and that voltage sag occurs by current, because of current draw. Now there are a bunch of factors that will affect how far a battery will sag and under load. So if we shift the car into neutral here, so I have zero motor power, 391 volts is where the battery settles at. And again, watch as I floor it, watch how far the voltage sags down. As the kilowatts go up, the voltage sags down to 338 volts. And so that voltage sag, that 53 volts or whatever, a voltage sag, that's about 15% roughly of the battery's resting voltage that it's dropping under load. And that's not really all that good for the battery. Now, let me explain a few things about this. First off, voltage sag is affected by a number of factors. One is the battery type. Tesla batteries are, they're cylindrical cells. They are high energy density, but not high power density. And what's the difference? Energy density has to do with how much energy, how many kilowatt hours you can cram into a battery of a given volume. So if you've got 1 cubic foot of battery volume and you've got whatever 10 kilowatt hours of energy, that is its energy density. Power density is how much power, how many watts you can draw off of that battery. So for instance, that battery, that 1 cubic foot battery, may be a 10 kilowatt hour battery. However, it may only be able to put out, let's say 20 kilowatts total under load. Now you may have another battery that's 1 cubic foot in size, in volume, and is only 5 kilowatt hours of energy, and you go, well, it's a worse battery. Well, not necessarily, because that battery may be able to sustain 40 kilowatts of output. So and that goes down to the C rating of the battery. C is times capacity. So if you've got a 10 kilowatt hour battery that can output 20 kilowatts of energy, that is a 2C battery, because it can put out 2 times its amperage rating, or its kilowatt hour storage rating. So the battery in illustration 1 that is 10 kilowatt hours and can put out 20 kilowatts of energy is a 2C battery. However, you can, the second example of a battery that is 5 kilowatt hours but can put out 40 kilowatts of energy, that particular battery is an 8C battery, and it is putting out twice the power of the first battery with only half of the volume. So it's putting out 8 times its rating. So we'll do this again, 390 volts. Now watch, I'll floor it. 260 kilowatts of energy. It's dropping down to 338 to 340 volts. So why is voltage sag a problem? Well, voltage sag, again, it occurs partly because of the C rating of the battery. It also can occur due to the temperature. Right now, admittedly, my battery isn't as warm as it could be. Let's see here. I can switch, go to this tab. The cell temperature is 63 degrees Fahrenheit. So let's go back to, see, there's the battery tab. Let's go back to my custom tab. There we go. So, so the battery isn't as warm as it could be. However, it is warm enough, and this isn't so much a test of the temperature of the battery versus how much voltage sag. It's an explanation of what voltage sag does to the battery. So, battery type will dictate voltage sag, and that is related to the internal resistance of the battery. So, also, as I mentioned before, temperature of the battery affects how much voltage sag, but it's primarily current. When you're drawing current off the battery, every battery will sag. Every battery, the voltage will sag when you draw current from that battery. It's just going to happen. Now, the internal resistance of the battery, again, affects it. The more internal resistance you have in a battery, the farther the voltage is going to sag under a given amount of amperage load. So you take that battery and you keep drawing load off of it, and you're sagging the battery, the voltage down. Now that voltage sag is hard on the cells internally. It's abusive on the cells, it really is. And so people talk about the longevity of their pack, and they usually mention things like not charging it too high or not supercharging too often. And I've brought this up too, that the health of the battery can be affected by not charging it too high too often. However, this voltage sag is very, very overlooked, and yet it is an important factor. So for instance, I've talked with a number of people that have performance Model 3s and Model S's, the P100D high performance Model S, that have talked about abusing the car and just flooring it at every stoplight, and how their performance is diminishing. And I've heard people online say things like, well, that's going to happen just over time. Batteries age. Well, they do, but here's the thing. They age very prematurely if you're drawing too much amperage off of them too regularly. So if you are easier on the battery, so let me illustrate this. So if you watch the screen here, I'll accelerate, watch the voltage. So we are currently with no load at 388 volts. So I will accelerate 20 kilowatts of energy. So roughly 20 kilowatts. So I've lost 4 volts. Voltage sag is about 1.3%. Now let's accelerate at 40 kilowatts. 40 kilowatts down to 380 volts. So we're looking at more like 3% voltage sag at that point. And so the more current you draw, the further you sag the battery. Now, a general rule of thumb, when I build an electric bicycle or electric go-kart, any of the small electric vehicles that I build, general rule of thumb is I want to see no more than 10% voltage sag under maximum load. That's typically what I shoot for. And if if I'm seeing more voltage sag than that, then one of a couple of things needs to happen. One of a few things. Either I need to use higher C rating cells, which have a lower internal resistance, or potentially more battery cells in parallel, so each individual cell is seeing less load, or I need to reduce how much current I'm pulling from that pack. Maybe set the maximum amp draw at a lower setting in the motor controller. And it's a personal rule that I have, rule of thumb. Now, maybe a chemist or an engineer can chime in here and let us know what their opinion is on this. But again, 15% voltage sag is a lot. Now, this also gets us into regen or charging. So I let off, I'm regenning 40 kilowatts, and you see the battery voltage increase. When you're charging the battery, if the battery is resting at, say, 350 volts, and you plug it into your household charger, it may raise it. It may only increase that 350 volts by 3 or 4 volts while it sits there under load, because it's only charging at a modest rate. However, if you plug into a supercharger, that 360 volts could climb up to 380 or 390 volts because you're pumping a lot of current into it. And again, that internal resistance, voltage sag also works in reverse when charging the battery. What you want to do is try to maintain as consistent a battery voltage under load, whether positive load, putting electrons into the battery, or negative load, which is drawing electrons out of the battery. And by minimizing battery voltage fluctuation based on load, positive or negative load, you will increase the lifespan of your pack. So this is an important principle, and I don't mean to get too technical with you guys. I'm not an electronics engineer, but this is just working with batteries over the years. This is something that I've found to be quite consistent. In the radio control industry, the early lithium cells were very low C discharge capable cells, and we would pull a high load on them and it would ruin the cells almost immediately. But if we were pulling a low load off those cells, they would last a very, very long time. So matching the battery to the load is important. A lot of people will discuss things such as, well, Tesla puts a large battery in their cars to give them a lot of driving range. Well, there's some truth there, but another facet to this is the larger the battery, the more cells that you put in parallel with one another, the less voltage sag you see under load, which is easier on the pack. That also means not only is it easier on the pack, but the larger kilowatt hour capacity the pack is, the more horsepower you can pull off that pack and make the car even faster. So generally speaking, for an EV, packaging size and weight is very key. So you want high energy density, which means you're going to have high internal resistance of the pack in general, which means you're going to minimize how much power you can pull out of that pack. So really it is a balancing act. So it's almost as though you can have long range in a car, but you're going to have high weight. Or if you want low weight and you want a low weight EV, you are generally speaking going to minimize performance, not just range, but you're going to minimize performance because of that voltage sag issue. If you want less weight in the car, you're going to have to use, and you want decent range, you're going to have to use higher energy density cells to keep the weight down per kilowatt hour, but that reduces how much power you can pull off the pack. So I believe this is part of the issue with the Porsche Taycan. That car is extremely heavy, ridiculously so. But Porsche wanted to pull maximum power off of their pack without harming the cells. Now Tesla pulls high power off their packs as well, but I haven't seen the voltage sag numbers for a Porsche Taycan, but they're using different cells than Tesla is, and my guess is that they're using higher C rating cells in their packs, allowing for higher current to be pulled with less voltage sag, and less damage done to the pack. Now, another thing that this affects is cold weather performance. So the colder the weather, the higher the internal resistance of the pack, and the less amperage you're going to be able to pull off the pack. I've noticed it both with my Tesla Model 3 that I'm driving now, and also with our 2014 Smart Electric Drive. With that car, if the battery pack is cold, it is noticeably much slower, much slower. So, but if we charge up the pack and then drive it a little and charge it, drive it, and warm up the pack, suddenly we have far more performance out of it. And that brings up another interesting point. The P100D, the high-performance Tesla Model S, when you select ludicrous mode, it will preheat the battery pack, and it will tell you that full performance isn't available until the pack is preheated. And that's because low temperature reduces or slows down chemical reactions, and a battery is a chemical reaction. You're trading a chemical reaction for electron flow. So the colder the battery is, the slower that chemical reaction is going to be, and the less power you're going to get out of the battery. So if you warm up the battery, you're going to get higher electron flow, higher current out of that battery, and greater performance. Now, the catch to this is lithium batteries typically like to be kept around 70 to 72 degrees Fahrenheit. And that temperature it's adequate to get decent performance out of the battery. But if you want maximum performance out of a lithium battery, you really want the temperature to be higher, maybe more like 90 or 95 degrees Fahrenheit, maybe even 100 degrees Fahrenheit. But that temperature is high enough that just the temperature alone is hard on the battery. So there's a catch-22 there, in that you either keep the battery at a temperature that it is chemically happiest with, but gives you a little less performance, or and if you pull high current off of that battery at a cooler temperature, it's harder on the cells because you're sagging the voltage, or you increase the temperature to get higher discharge out of the cells, and that will give you less voltage sag and more performance, but the high temperature is hard on the battery there. So it is and that's why it's difficult to get high performance out of high energy density cells. Now, high power density cells that have a higher C rating or a lower internal resistance, you can pull high current off of those cells with less voltage sag. You can do it at a lower internal temperature, and it seems like a win-win, except higher C rating batteries are far less kilowatt hours per cubic foot of volume, and therefore you're going to also have higher weight per kilowatt hour, and typically higher C discharge cells are going to cost more per kilowatt hour of energy. So there is a balance there. And with the next gen Roadster, people talk about, oh, it's wonderful that it's got a 630 mile driving range or 620 mile driving range, whatever it is. Well, Tesla wasn't shooting for high range out of that car. What they're shooting for is it needs about 1,600 horsepower to accelerate that car to 60 miles per hour in the 1.9 seconds that it's rated for. The only way to get 1,600 horsepower of discharge potential out of Tesla's high energy density cells, high internal resistance cells, is by giving it a 200 kilowatt hour battery. So that 200 kilowatt hour battery, a side effect of having such a huge battery to give them the high performance they need, is a long driving range. So this is a very interesting, discussion, because there's so much involved here, and as with everything in life, there's always trade-offs and there are always compromises. So I hope this gives you guys a better understanding of the performance. So let's do this again. 386 volts. Let's pull current. 338 volts. Sagging it down. So again, you can see the voltage sag that's there, and also under Regen, the voltage increase. And we take the load off, and we're hovering at 387 volts. Give it a little bit of load, and it drops down to 369 volts. So you can see that the battery fluctuation, then under Regen, it goes back, the voltage goes back up again. As you fluctuate current going in and out of the pack, it sags or increases. It pushes the voltage above or below the resting voltage of the cells, and that pushed voltage up or down is hard on the cells. So in closing, basically, be kind to your pack. Also, I have a long-range rear-wheel drive car. This car is only pulling about 320 horsepower off the pack. This same pack is what's used in the Performance 3, and it's going to draw far more amperage. And the voltage sag on a Performance 3 is going to be much more extreme than on my car. So those of you with performance cars, just be aware that every time you floor it, you are diminishing some of the battery's life, at least a little bit. So bear that in mind. Every time you floor it, when you floor a gas car, you're loading up the engine, and it's hard on the engine internals and the drivetrain and that, and you're slightly diminishing its lifespan every time you floor it. Same thing it can be held true for electric vehicles as well. It's hard. It is hard on the motor to a certain extent and the inverter, but it's much harder on the battery. So if you want maximum life out of your battery, then save those full throttle excursions for only occasionally. I mean, by all means, enjoy your car, but don't be flooring it at every single stop sign. Wait till it's, more necessary, when you've got someone next to you that is trying to get around you, or you've got someone in your car and you want to have fun and show them the car, or you're on a back road and enjoying yourself. But don't floor your car at every single stop sign, because it is very hard on the battery pack. All right, so that's it. It was, I'm sure, a lot to digest, but again, you don't necessarily need to know all the technical data behind the scenes. I don't even know all of it. I'm just a layman. It's just something that this is data that I've picked up over the years of working with lithium batteries. But, I wanted to show you guys this just so you can have a better understanding of how to increase the longevity of your EV, and also just a little bit of what's going on. I also think it's cool that I have access, or that we have access to this data through third-party manufacturers that are making the OBD2 adapters and the Scan My Tesla app and other products like it. It's a very useful tool. So anyway, thanks for tuning in, guys. Give me a thumbs up. Click the notification bell and subscribe. If you have any questions, by all means, let me know in the comments section below. And so I think that's it for today. And as always, stay charged.